So NetBeans is one of the compiler, very popular compiler. The other actually, these are two very popular offline compiler. So basically, you can actually write your code on your local laptop, and you can compile it over there, or compile over there. And the compiler in the Zybook is an online compiler, so you have to make sure you have an internet and log into the Zybook, then you can use the online compiler. And I think the other very good online compiler is um, now is something called I can introduce that compiler is the let me actually show you what it is. Um, uh, it's called it's a website. Oh, REPLIT. In the Google, you can quickly search it, and you can find out it's a very uh, convenient to use. Let me actually show you what I have now. So this is a website of IEPL.IT, and so if you try to use this, you first need to actually type. You can search the okay. So you can type IEPL.IT. Then it's a website, and in order to use it, I think you have to actually sign up. You need to create an account. Uh, Now you can create a free account. You don't have to pay because it's a very nice account for actually learning the computer language. So you can yeah. So you can create for example, if you use the uh, depending on which language you're gonna use, I can say see all languages. Click. You can see Java. Um, so you can create something called REPL, and so you can click it and create it. And this is something I just created. Okay, uh, so it's like some kind of the middle pane is for you to edit your source code. The right side is the console, so you can actually run your code. For example, if I have a Java code like this, um, so I can just say, oh, import X. So I can just say, so I can say you enter the uh, X. So if I run it, so because I use a scanner, I create a scanner called MyScan. Uh, so I can just and then I just call MyScan dot next int. I just enter the next value at the prompt. So you can actually say 4. I type 4 over here. Uh, then I hit enter. So, oh, I think I just need to save it before I do this. No, it's a Okay, so 6. I don't know why this still gave me this. Oh, I think I know what's going on. I use the Java C. I'm still compile the main.java and
Is it working?
I don't know. I changed the string from hello world to untitled. Then it still actually show the things called untitled. So let me still say hello world 4. So it looks like it's actually compiling a different one. Let me see what's uh, okay. So let me see. This is the code, my new code. Oh, uh, go to my. So let me see. Try to run again. Just compile. Oh. So if I do the system, okay. Let me change this. If I okay, I can admit more people coming. So let's say x equals 6. Let's see. So I forgot to. I also comment the declaration of x first. So that's why. It's kind of slow, but that's typically what happens for the online compiler. It depends on your connection. Why it's so slow? But you can actually create this REPL.IT, so you can use this online compiler. It's very convenient. But I need to figure out why, if after I change the code, that when I compile it still actually print out the older code. So what's going on? Let me stop it. looks like it didn't change the code. Okay. Yeah, it's still running the old code. So okay, so I figured out later, but this is actually a good one. I used this before. It works very well, but I don't know why when I change the code and I run the code again, it just actually refused to change and it still actually run the old code. So it still actually, it looks like it still recognize the scanner thing, even though I already
So you're
deleted.
saying that you changed. So you're saying that you changed everything, but it still shows the old code.
Yeah, it still sees the old code. So it still
I
have,
think you. I think you might need to try refreshing. Have you tried doing that?
yeah, you need to
Yeah.
refresh.
It's either that or you forgot to put some sort of extension.
What I do this. Okay, let me just refresh it, run it. Yeah, looks like it doesn't help. It still actually sees the old code. So let me actually figure that one out. But yeah, you can actually try to log into the IEPL.IT. This is one of the uh, online compiler I use, but I cannot explain why this happened right now. But it's actually working, um, working code. So this is something you can think about. Uh, the NetBeans and the Eclipse is just basically for offline compiler. So, which is in the current situation, the classroom setting, it's not really convenient for us to use them. One good thing about IEPL IT is that it allows to have a group. You can actually share the same code by the group, so everyone can change the code and then run it. So not just one. So you can a couple of people can share it. As far as the number is smaller than 10, if you have a 10 people or smaller to share these code, it's free. This is free. But if you actually exceed the number 10, they're gonna charge them money. They have a restriction. They want us to pay the monthly fee and join the you know some kind of membership. But if you have a small group and you can actually exchange some idea and share the same compiling screen, so you can all actually work on the same code, so which is kind of good. So that's a reason why I don't create an account for the class, because that way I have to pay. But if in each individual you can actually create the account and you can use the tool. Okay, let me start to continue with the topics. I plan to actually complete the chapter 1 and start the chapter 2, so hopefully we can um, finish um, the module 1, which consists of 4 chapters. We can complete the module 1 in 5 weeks. Okay. Um, so let's actually. Oh, last time we talked about the comments and the white space, and there are two different comments. You can use single line comments, which basically you use the double forward slash, and the multi-line comments. If you have a whole bunch of comments, like if you write uh, a function and then you want to actually put a description for the function, you can use multi-line comments. Also, for the white space, I just mentioned that technically Java typically going to ignore the blank space. Okay, ignore the blank space. Um, so if you actually say x equals 2, no matter how many space you're going to put between equal and the 2, then Java simply choose to ignores most of the white space, except if you put the space in the printer statement. Okay, in the printer statement, if you just say system print. Now you can put the string, or sometimes called a string liberal. Okay, you can put the string in there, and in the string liberal in the printer statement, then each space you put in there will be printed as it is. So if you put a 2 space, 3 space, it will print the 2 space and the 3 spaces. That's just keep that in mind. But in most of the Java statement, the white space will be ignored. Even like you have you press the enter a couple of times, you leave a couple of actually white lines, and Java gonna basically choose to ignore these white spaces. And also we mentioned that the in most of the Java code, you may experience the errors and the warnings when you compile your code. You finish the compiling your code, and you experience you're probably going to see some kind of error message. So the error message, so it's unlikely that you can write a perfect Java code without any error message. If particularly when the program is so big, so you're probably going to experience some kind of error messages. But it's it's not unusual. So also when you actually see error messages, you're probably going to see the line numbers. So Java try to point out which line has the error. But just keep in mind, the Java compiler is kind of like a best guess. Try to do the best guess for where the error happens. Okay, because it's technically impossible for the compiler to figure out what's exactly wrong. But if the Java compiler say, okay, in line number 26, there's an error, such an error, and you check the line number 26, you're probably not going to be able to find any errors in line 26. Now, it's likely that the error actually happens before line 26. Okay. Now, it's because, for example, if you actually write some kind of code like x, say int x equals 2, y equals 23, or xy, you can declare. And then you actually miss the semicolon over here, okay, in this line. But Java probably not going to be able to point out, okay, there's an error here, because Java believe if Java don't see the semicolon, Java going to believe, okay, your line hasn't finished yet. So they're going to treat the y as the continuation of this line. So you're going to actually, when the Java compiler going to believe this is x2, y equals 23 semicolon, and then Java find out, oh, I'm confused because why this happened. There's two equals. So Java gonna point out, oh, there's definitely an error here, but you cannot see any errors in here. But it's because of the error happened before it, and the Java continue to work on this, and then eventually detect the error in the next line. So, but the Java going to point out there's an error in this line, but it's actually happening in this line. So you just keep that in mind, because when Java didn't see the semicolon, I don't think Java is smart enough to figure out, oh, you're supposed to have a semicolon over here. No, you don't. So Java going to continue to think the line's not finished yet. So you're going to treat this y as the next character in this line. So then they find out some kind of inconsistency. and then point out some error message. So in that case, if error message if error message is pointed out, you know, it may actually happen in the line that Java just pointed out, or maybe error actually happens in the lines before. Okay, just keep that in mind. So as a good practice, I always believe that you should actually, every time when you write a couple of lines of Java code, compile the code, make sure there's no error, and then you can add one more lines, two more lines, add a couple of more lines, and then compile the code. So you should actually frequently compile the code. That way, you can reduce the possibility of error message. Because some people say, oh, I just write the code very carefully, then I can just create the code and like a 100, 200 lines of code, and then I just do the compiling. And then if you're probably going to see an error message. And then once the error happens, like an error happens in line 200, then you never know where the error going to be, because it could be in this 200, line 200. It could be line 199, could be line 198. So this is a lot of, it's very painful to find an error message in a very, in a very big code. Now, if you actually compile frequently, that's a different story, because once you compile it, you have no error message, and then you add 10 additional lines, and then you compile it again. You see the error message. Now you are pretty sure that the error happens in the lines you just added after the previous compiling, because there's no error in the previous compiling. So error happens in this. So you can narrow down the area, so you can easily find out where the error happens. Okay, so that's why just try to compile frequently. Okay, now the other kind of error is called a logical error. Logical error is actually more difficult to diagnose. Logical error is actually, it's not a syntax error. There's nothing wrong. You write everything correctly. You put the semicolon at the end. You put everything right. But logical error is actually the error message that eventually going to give you the wrong answers, even though you put
So,
yeah.
okay, so is this kind of related to the post that I made on the discussion board? Like you did, it seems like you're doing everything right, and then an error appears to direct you what you've done wrong, and then you try to fix it from that point, but it's still wrong.
Yes, it could be that case. So that's why I need to look at your case, particular case. So I need to see the code to see what is really going on. Now, the bad thing about the Zybook compiler is Zybook actually does not separate the compiling and the run. You know what I mean? If you use any typical compiler, you're gonna do the compiling, and then you're gonna run it. But Zybook compile this process, compile, run together. But only you have a syntax error, then the Zybook is gonna stop, point out what's wrong. But if there's no syntax error, like this logical error, it's kind of difficult to see it. So you need to check the code, because the logical code is not a syntax error. It's probably something wrong in your formula. This has nothing to do with the code. It's actually probably your formula and your way of organize things. So, for example, if you actually say x, import value of x using the scanner, import value of x, import value of y, and you calculate z equals x divided by y. Now, this has a potential, because the compiler will never point out any error, because there's nothing wrong with it. You import the value of x, you import the value of y, and you do the division. So x divided by y assigned to z. Nothing wrong with this. However, when you execute it, you may actually experience an error message, because if you actually import the value x equals 5 and the import the value y, you import 0, and then you experience something like 5 divided by 0. So that's wrong. mathematically, you cannot divide anything by 0. That's logical errors. Okay. So I don't know exactly what errors you have, but I need to figure it out. So if you have a time after the class, then we can actually check your code to see what is your problem. Okay.
Yeah, next time I run into that issue, I'll show you an example.
Okay.
Because like I already fixed the issues that I had previously.
Okay. Yeah. If there's no compiler error, you're pretty sure it's a logical error. So that logical error could be, it's not necessarily a computer language problem. It's probably the whole algorithm, the whole actually expression you put in there is wrong, but the compiler did not catch it. Now, one of the example is like in this case. So let's see. Like in this case, so the program might mean you actually want to type number of beans times number of jars, but you actually put the number of beans plus number of jars. There's nothing wrong with the language, but your formula doesn't actually mean this. So so if you say, for example, like in this particular example, like you have 8 beans in each jar, and then you have 10 jars. So that means 8 beans in each jar, and you have 10 jars. That means 8 times 10. You have total of 80 beans. But you actually accidentally put the number of beans plus the number of jars. That means you have 8 beans plus the number of jar, which is 10. You got 18. That doesn't make any sense, right? So that's a logical error. The compiler never know there's an error. Okay. And also during the compiling, you may experience a lot of compiler warnings. A warning is not an error. In many times, warning is okay. So you can still run the code well. So you can pass the compiling, you can run the code very, very well, but sometimes warning could be a warning, um, like some of the compiler, a very smart compiler may report a warning, say, warning, division by 0 is not defined, something like this. The compiler is still going to let you go. But when you actually run the code, if you run into like a division by 0, then you got an error. That's called a runtime error. Now, typically by default, Java compilers don't print every possible warning. So that's the problem. But you can, if you use Java C, the command-based compiler, then you can probably see the if you put a particular option like a dash XLINT, then it will actually print out all the possible compile warning. So even though you don't have error, you're gonna print out a warning. As I say, warning is not, in many times it's not a problem, but it's still a good practice to write a program that to compile without warnings. That's always the goal. But even if you have a warning, don't worry, it may work. It's still most of the time it's still gonna work. Okay, so now let's actually talk about section 1.5, computers and the program. Now, so I'm actually not going to actually spend much time on the rest of the chapter, but I'm going to actually give you a brief overview of these computers programs. Now, the computer actually, the computer programs is closely related to the computer itself. When I say this, what I mean is that you need to know how the computer was built. Now, the early computer is actually built by, it's an electronic device. In a modern computer is actually electronic device which consists of a whole bunch of something called integrated circuit. Integrated circuits. Now the integrated circuit is kind of like a silicon wafer or silicon component. Okay, inside the silicon component wafer, it consists of millions or billions of small switch. Okay, it consists of billions of small switch, and these switch are not just like a switch for the light for your light. So you have a switch. You can pull the switch up, down, push the switch up and down to turn on the light, turn off the light, and that's a switch. But this is, the electronic switch is basically it's controlled by, the electric flow. Okay, so it's controlled electronically. So so the electronic switch. So rather than by a person moving the switch up and down in the electronically controlled switch, normally a positive voltage at the control input allow electricity to flow. So if you apply the positive voltage, like let the electricity flow, then that's on. Now if you stop the actually voltage, then it's off. So it's controlled by electronics. So it's like and then that's a switch. So you can actually close the switch to let the electricity flow, or you can open the switch to turn off the switch. But this switch is not controlled by your hand. This switch is controlled by another electricity. Okay. Sometimes people apply the electricity here. Then if it's on, then it's closed. If it's off, then the switch is off. So it's controlled by electricity. Okay. So if you apply a voltage, so that means it's on. Then normally we actually use the number 1 to represent on, number 0 to represent the 0 voltage. There's no electricity running on this wire. So 1 is on, 0 is off. So that's the reason why we call modern computer system a digital computer, because it consists of millions of billions of these switches in the small silicon component. Now once you build this component with a whole bunch of switches in there, you can build a device, and this device may have some input and may have some output. I may have some input here and some input output here. Okay, so here's the input. Okay, now each input actually has actually a small wire, and each wire you can apply a voltage, a signal. If you apply voltage, let the electricity flow into that wire. That's represent number 1. And then the second wire, you can apply voltage. And the third one, you don't apply voltage, so you make it 0. So now you can have an input 1 1 0 1 1 1 1 1. Okay, then you have an input here. So you have a 1 0 1 1 1 1. So you can have an input value, and then inside this, because of they depend on the input, then the switch inside are going to be, some of the switch going to open, some of the switch going to be off, some of the switch going to be on. So eventually you're going to do the work and generate output. The output could be 0, 0, 0, 1, 1, 1. The output could be 1, 1, 1, 0, 0, 0. So here's the input, here's output. Okay, so that's the integrated circuit. Okay, so because of this, so the computer basically is an electronic device that takes certain of the electronic signal. It's either basically a sequence of electronic signal that represented by the binary numbers. The binary numbers could be 1 or 0, 1 or 0. So basically it represents whether you apply a voltage or not. If you apply voltage, it represents 1. Does not apply voltage, it represents 0. So it's basically a device that takes, like this, you take a sequence of binary numbers. Okay, when you take a sequence of binary numbers and you have a sequence of binary numbers out, okay, so that's basically perform the job. Okay. So these circuits, initially the circuit, these circuit boards are very simple. It may actually build a couple of switches inside. And then they increase the number of switches from 100 to 1000 to 1 million. And now the modern actually integrated circuits may actually contains like billions of switch. Okay, so the distance between these switches are so close that they actually have to use some kind of nano technology, so that these switches are actually only a couple of nanometers apart. So it's so close. You need a very high electronic actually microscope to see it. Even though there is an electronic microscope, you still cannot see it. It's too small. So that's the modern technology. The circuit became increasingly complex, leading to the first electronic computers in 1930 and 1940. And now the modern computer system basically are built of these circuits. Okay, so now in order to control this device, you need to have an import of these binary digitals, right? 0, 1, a sequence of binary digitals. And these we call the program. Okay, so you can have a sequence of program like 0, 1, 1, 0, 1, 1, 1, 1, 1, 0. Okay, that's a sequence of binary digital you as an input, and then goes into the computer device, and then the computer going to do the job and generate output, the result. Okay, so these are called the instructions. So you give each of the device a different instruction, they're going to perform different jobs. Because if you, for different instruction with different combination of binary numbers, 0, 1, 1, 0, 1, 0, 0, 1. So these are different combination of 0 and 1s, going to actually eventually perform different jobs. Because it's going to eventually leading to the different actions for each of the switch inside these circuits. Okay, so modern computers actually consist of different devices. One is the processors, and sometimes we call it CPU. Okay, now these CPUs are also it's a circuit. It consists of a whole bunch of switches, and these switch the processor is going to take instructions. Okay, it's actually it's a circuit that are created to process a list of desired calculation with each calculation called instruction. How can I do the calculation? Then you need to define the binary sequence, the pattern of binary sequence. Now, different pattern basically defines different instructions. Okay, a memory is also a circuit that can store binary digitals, zeros and ones. So it can store zeros and ones in each of the series of thousands of addressed location. So the memory is organized into a series of addressable addressed location, and each of the addressed location we call it a cell. So the first cell in this sequence is address 0, 1, 2, 3, 4. This number 1, 2, 3, 4, 5 is called the address of the memory. So when you say I store a number in a memory location 1000, that means if this is a memory 1000, so I actually put the cell basically consists of addressable one, which contains each position going to actually store a bit. A bit basically can store either 1 or 0, or 0 or 1. Okay, so you can, so if each typical computer memory has a cell which contains 8 bits. So that means that I can store a sequence of 8 binary numbers. So for example, I can store 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. It's 8 bits. So then I can store this number in this cell. Okay, so this number, people can interpret each of the something called a bit pattern with some meaning. That's called encoding. Okay. If you store a number, then this is a number. So you can directly convert this binary number into a decimal number. So that's what the memory do. So instructions are stored in a memory. So instruction consists of a sequence of binary digitals. So if the instruction requires like 16 digitals, then you just need to store, you need 2 cells, because each cell is 8 bits. You have 16 bits instruction, you can store into 2 cells. Each cell consists of 8 bits. So then you can actually install a sequence of the binary bits called instruction into the computer memory. So instructions are stored in a memory. Okay. So basically, computer is a processor interacted with the memory. So that's the processor and the memories are the main components of the computer system. Okay. Now, here I can give you an example of the sample instruction. Okay. Now, technically, instruction is just a sequence of binary numbers, but people also use some kind of it's called a mnemonic form. So instead of using the binary numbers, they use some kind of mnemonic form to represent each of the instruction. For example, this is called add. Okay, add x, comma, number y. What does that mean? That instruction basically means I add data in memory location x. So here's the memory. So this is the memory location. Remember, memory location is the memory address. So x could be 100 because this is a 100 in the sequence. So add data in a memory location x to the number n, to the number num, num, okay, to the number num. So, and then store the result in location y. What does that mean? Okay, that means, sorry, I don't know, I hit the key somewhere. Something just come up. Okay. Now, so for example, if I say add 10 so in this case, I replace x with 10. So that means I'm going to add a number stored in the memory location 10. So let's say here's the memory. It's a 7, 8, 9, 10, 11, and then 12. So this is actually the memory address. So I add the data in the memory location 10. Now, what is the memory location data in the memory location 10? If the memory location 10, I store the data, the value I add is 5. So then I basically add 5, which is in memory location 10, to the number num, which is 9. So basically, I am going to add 5 to 9. 5 plus 9, this gives you 14. And then store the result in location y, which is 11. So I add 5, which is in 10, to 9, which is 14, to and store result in 11. So the result is 14 in 11. Okay, so this is actually the computer going to perform. Okay, if I gave you the computer this instruction, because in the memory location 10, the value is stored as 5. Okay, so this is actually subtraction, multiplication, division, and this is called a jump. You're going to jump the location. Okay. So this is another example. Multiply 97. You don't multiply 97 by 9. You actually multiply the data, the value stored in memory location 97. Okay. To that number 9. And then store the result in the memory location 98. Okay. So these two are memory addresses. Okay. Now, this is actually the kind of format of the instruction. Okay. Now, actually, the computer instruction is even actually it's not even like this. You know, the instruction is just like this. So here, 011 specifies a multiply. So actually, this is actually the actual, people interpret this 011 as multiply. So actually, this instruction basically is, if you look at the previous one, it's just like a multiply 1100001111000001. That's a number. This is actually the number, and this is another memory location. So these two are memory location. Okay. So now if you convert this binary number into a decimal number, so 110001, this is actually 97. Okay. Now the second one, let me actually erase the number. So this is 97. Now this is actually 9. And this is 98. And this 011 basically means multiply. That's the encoding. That I just interpret this as a multiply. Okay. So this is actually MUL 97998. So this is actually like this command, but I actually has an actual value. So this is actually the real computer instruction looks like. Now, each of this number is binary number, and when actually you import it into the computer, you basically apply, say 0 means okay, I don't, in this import while I don't apply the voltage, and 1 means, oh, I apply high voltage, high voltage, high voltage, high voltage, no voltage, no voltage, no voltage, no voltage, high voltage. So you import this, and this instruction, the CPU going to perform the corresponding job. Okay. So the programmer created sequence of instruction. This sequence of instruction is called a program, or we call it application. or just app. Okay. Now, this is actually the called machine instruction. Okay. Now back on this, we normally call it assembly language. Okay. It's very close to the machine code, but it's, instead they use the ADD in place of 001. You use MUL. It means multiplication instead of 011. Okay, because it's easier for us to understand ADD than 001, right? That's called assembly language. However, the computer still cannot, even the assembly language, the computer cannot recognize. Remember, the computer only recognizes the digital signal. It's 0101, the digital signal. So if you put ADD, what the hell is ADD? The computer does not recognize. So then we need some kind of translator to translate this assembly language into the computer machine code 0101, the digital code. And that translator is called assembler. Okay, assembler. Okay. So now the assembler is actually used to translate the assembly language instruction into the machine code. Okay. Now people still find assembly language is easier to use than the machine code, because the machine code it doesn't make any sense unless you actually work on this device. Because you are electronic, you're electronic engineer. Why? Because the computer accepts this instruction 010110, because this instruction gonna actually enter into the while, and it's gonna pass through each of the switch. The switch gonna actually open on and off to generate a different result. It's kind of a logical actually operation. You know that, but for other people it doesn't make any sense. 0110, what does that mean? Okay, so that's why we create the assembly language to make it a little bit easier for other people to understand. But it's still, assembly language is difficult to understand. It's very difficult to understand. So that's why in the early age, like 1940s, 1970s, or 1950s, people just view computer scientists as a group of people who are extremely smart. They can working on the devices. They can speak a kind of language no one can understand. Okay. And then they find out this is not so good. So in 1960s and 1970s, people start to use some kind of language called high-level languages. Okay. The high-level language is basically just say, if I do the addition, I want to add two numbers. Why I want to use this? Because this is going to actually ask us to pull the number from the memory location and add this number from this memory location into the number and store into another location. Now, when people actually use the computer, most people just feel like, I don't want to know any details. Well, I need to get the number from the memory location. All I want is, I want to add two numbers. Okay. If I actually say I import a number x equals 2, I import another number y equals 3. I want to x plus y, so I got 5. So all I need is actually do the addition. So that's why the high-level language is introduced. In high-level language, people actually, basically the high-level language was created to support programming using formulas and algorithms. For example, I use this formula. F equals 9 divided by 5 times C plus 32. So if I actually given a number C, if C is 100, then I can calculate the f. So it's like a formula, like a function. By the way, do you know what is this function supposed to do?
Does it convert Fahrenheit to Celsius?
It's the opposite. Convert Celsius to
Oh yeah,
Fahrenheit.
sorry, yeah.
Yeah. So yeah, because in this world, people use two set of actually measurement. In United States, we use Fahrenheit, so which means 32 is a freezing point. But in rest of the world, in like even Canada, they use Celsius. That means, okay, freezing point is actually 0. So if Celsius is 0, that means Fahrenheit is 32. So that's the conversion between. Now, it's a good example that we use the computer to calculate this, to convert this Celsius into Fahrenheit. Now, people want to say, all I want is this, the formula. I really don't care where you store this number C, in which of the memory location, right? I don't care. I just want to compute this. So then the high-level language basically hide the details of this storage or this computer hardware where these numbers are stored, just to actually allow people to focus on the problem. So that's basically what the high-level language is. The most well-known high-level language was Fortran. It's called a formula translator, and the algorithm, algorithmic algorithmic language. Formula is widely used in computer in the United States, and algo is used in Europe. These are two different languages. People can use. So then, however, when you write the formula and ask a computer to do it, the computer cannot do it, right? As I just mentioned, that even for the assembly language, a computer cannot recognize it. So that means these formula need to be translated into the machine code. You still need to translate it into machine code, like a 0110, the binary code. So that translator is called a compiler. Okay, so you need a compiler to translate high-level language into machine code. Okay. So Java is one of the high-level language, and the C, C++, even Python. Okay. Now Java is kind of special. You basically translate the language into some kind of called a bytecode, which is actually, it's not in the middle. It's actually in the middle. It can be recognized by some kind of virtual processor. And then you don't have to translate it into a particular instructions, because each instruction is related to the hardware. For example, if you use the PC with Intel CPU, the Intel has its own set of instructions. Okay, if you want the Intel CPU to perform the job, you need to compile into a set of instructions that the Intel CPU can recognize. Okay, because Intel CPU has its own logical design inside the circuits. And the AMD has its own different set of instructions. So AMD has different set of instructions. So in this case, the compiler need to figure out what I need to compile into, what kind of instruction I need to create, depend on the type of computer. But the Java allow us to compile into something called a bytecode. And then you can install this actually virtual machine on each of the computer. So the Java is actually run on the virtual machine. So that's why the good thing about the virtual machine is it's portable. As far as the PC has a virtual machine built in the computer, then you can run the Java code. So the disadvantage is it's kind of a slow because the performance is going to suffer. Okay, that's something we're going to actually mention that later. Okay. Okay, so I'm not going to actually spend much time on the computer tour, the section 1.6. I want you to read the Zybooks, and perform the exercises in section 1.6. The computer tour basically tour the computer hardware, and tells you a little bit about the computer history, and tells about different components inside the computer system. Okay, as I say, the computer consists of input-output devices, storage, mostly, and also memory. Okay, now this many times people also view memory as a storage, but the storage as a memory is not the same as storage as hard disk. The hard disk is mostly called a non-volatile storage. That means non-volatile basically means if you store the data in that storage, like a 0110, the binary digitals into that storage, non-volatile storage, then it's kind of sort of permanent. So even you turn off the computer power and turn back on, the value is still not going to be changed. Okay, for the memory, it's kind of different. Memory is also called the random access memory. It's called a RAM. RAM actually temporarily hold data read from storage, and it can be accessed much faster than disk. However, RAM is volatile, so that means everything stored in the memory is temporary. Once you actually finish your computing job, you want to actually turn off your computer, and then when you turn back on, everything stored in the memory will be gone. So they will not be actually permanent. So that's a difference between storage and the memory. Okay, and then we also talk about the processors and the clocks. The clocks basically measures just how faster the process is going to be. So please read each of these components in section 1.6 and perform the exercises. Now the last section is about the different languages, and based on the survey in June in June 2019, so they listed the different language and the percentage of these languages are used in industry. Okay, and Java is still the number one. Okay, C language is next, and Python is the third. Okay, which consists of 9%. However, the Python, because Python is actually relatively new language, so the percentage for Python is growing, and the percentage for Java is going down. So that's the reason why in our computer science 1 we start to use the Python. You know, a couple of years ago, we actually covered Java for computer science 1 and computer science 2, but now we actually switch to Python in computer science 1 because Python is gaining its position, because in industry Python becomes more and more popular, particularly in the cloud computing. You know, people actually start to use Python and some other language. Okay, now Java is still the most important language, but the popularity is actually it's going down, and we expected that sooner or later maybe Python will replace Java as the number one language, but not at this moment, not in 2019. Okay. Okay, so that's pretty much all for the chapter 1. So please actually, if you haven't finished the chapter 1 exercises, please actually do so. Now let's jump to the chapter 2. Okay, so let's actually start the chapter 2. I may not be able to finish much of the chapter material. I'm not going to actually spend much time on chapter 2 because chapter 2 is about the variables and assignments. Now, there are lots of similarity between the Java variable and and the Python variable. So if you actually already learned the Python language, you know exactly what the variable means. And the only thing I want you to realize is that the difference between the assignment and the equal. Okay, in computer language, if I write x equals 2 equals 5, that's assignment. Okay, assignment means basically I just reserve the space. X is a variable. When I declare a variable, I reserve the space in the memory called x. When you do the assignment of x equals 5, I actually assign number 5 into x. Okay, so that's the assignment. So it's not the same as math. Like x, when I write x equals 2 in math, that means x is the same as 5. But in computer science, it means assignment. Language, it means assignment. So because of this, some of the expression, like a statement like x equals x1 makes some sense, right? Because in math, this doesn't make any sense. Why x equals x plus 1? X plus 1 is always 1 more than x, right? It's not the same. So why this is true? But in computer language, this definitely makes sense, because this means it's, you actually check the value x. Okay, for example, the x is 5. So that means I'm going to add the value stored in x, which is 5, by 1. So 5 plus 1, that's 6. And then I assign 6 to x. So that means I actually put the result 6 into x. So this basically x equals x plus 1, just do the incrementing. So you're going to override the 5 by 6. So after this operation, x is going to be 6. So this makes sense. But in math, this doesn't make any sense. X equals x plus 1. So you can cancel the x on both sides. You got 0 equals 1. That's nonsense, right? So that's why you need to realize the difference. But the variable is the same between Java and the Python. And also variable declaration. Variable declaration is a statement that declare a new variable, specify the name and the type. Now, when you actually use the variable in Java, you have to declare it. Okay. Otherwise, if you say x equals 2 and you compile it, it will give you error message. So you have to compile it. So you need to declare if x is actually integer type, you're going to say int x. Then x is declared as integer, and then you assign integer to x. That makes sense. Okay. Now, talk about the variable declaration. You probably actually, if you remember Python, do you actually see any C declaration in Python? Sometimes in Python, looks like if you type x equals 2, it's gonna work, right? Y equals 3, z equals x plus y. It's gonna work. You don't need to declare this. The reason for this is because, in Python, you don't have to declare the variable before you use the variable. Okay, you declare the variable when you actually use it, when you assign a value to the variable, then you actually declare the type of the variable. So that's why it's different. In Java, before you use it, you have to declare it. In Python, you don't have to declare it before you use it. You declare it when you actually use it, you declare it. Okay, so that's why Java is called a statically typed language, and the Python is called a dynamically typed language. Why? Because you can use you can, when you actually see x equals y, and then I know x is integer type, and the next time y equals 3, z equals x plus y, then you can do this, and then suddenly you can say x equals 7.3, 7.31. So it's not an integer anymore, and then Python actually declare x as a real number now. It's not an integer anymore, because here you declare as an integer. Here you can change type. So that's why it's called dynamically typed. Now in Java, you cannot do this. If you declare X as integer, then you cannot declare X as any other type. So X is going to be integer type throughout the whole program. Okay, that's called a statically typed language. That's a major difference between Java and Python. Okay, now 2.3 is about identifiers. This is the same as Java, Python. Python identifier is actually, it's a name created by the programmer for items like variables and methods. That's called identifier. So please actually read this chapter 2 topics and perform the exercises. And I think this chapter 2 is pretty much similar to the materials we learn in Python. Okay, so the variables, the assignments, the identifiers, these are pretty much the same. So please actually work on these chapter 2 and perform the exercises. If you have any problem, please let me know. And next on this Friday, I'm gonna organize this group. So because I know I in the second announcement, I actually formed these 3 groups. I want you to have some kind of group meeting to chat each other, to get to know each other, and eventually you're gonna work as a group. So if you have any questions, you can bring the question in the class. Okay, the discussion forum, the discussions in the Blackboard are gonna be used to express your opinions, your questions, or anything. Okay. So, okay. I think that's pretty much all for today. So, do you have any questions? And also, I changed the due date for the chapter 2. So if you still have a question in chapter 2, you can bring up on Friday's class. So also, when I say the due date is February 5th, that means it's the end of the day. Okay, so you can actually submit anytime before the midnight on that day. So technically, if you have any questions, you can still ask on Friday's class, and then you can continue to finish up the second assignment 1B, and before the midnight. Okay. Questions?
We're supposed to meet as a group this week.
No, you still come to the class, and I will give you time to meet during the class. Probably like I give you like 15 minutes or something. So the first it could be like your team building, or you can just have some kind of a social. Because unfortunately, we cannot meet actually physically meet, but we can still meet face to face virtually. But so okay, so
We could probably figure out some ways to, like, I don't know, reach out to each other in case the time comes closer.
Okay, yeah, we could do that, based on the how things are going. So I hope that this COVID is going to be going to be gone in the middle of semester, or we can get the vaccine, and then we can change our schedule. But at this moment, the school is very strict on this, so on the rule for this.
Are you gonna post the next set of homework problems soon?
I will do that. I will do that. Either today or tomorrow. So please keep an eye on the Blackboard. And also on the Zybooks. Yes. Okay. So enjoy the snow, and we expect to have a snow this afternoon and tomorrow morning. So, well, have a good day.
Have a good day.
You too.
Good day.
You too.
Bye.
Thank you, Professor. See you later.
See you later.